we have defined our field tensors F and G. We want to do actually electrodynamics with that. In particular, let's see if we can reproduce Maxwell's equations. That's why I wrote them up there before the lecture. So, first step to do that, obviously, is that somehow we need to probably generalize what is rho. So we need to kind of connect the field tensor to rho and the current density. And the first thing you might expect that we want to do is, well, we want to write everything in 4 vectors. J is a 3 vector, but so there's J in rho. Rho is just a scalar that we maybe combine these into a 4 vector. To see that how that makes sense, if we have rho as charge per volume, if we Lorentz transform with some Lorentz vector gamma, what happens? Rho, the charge won't change, the volume will be Lorentz contracted. So let's say rho bar will be gamma times rho. And but the charge density you can always write as rho times V. And the same transformation will apply there, right? J bar will be gamma times J. So as a generalization, if we kind of write a 4 vector, that's J mu, we can write the charge in the time component and J down here, something like that. To account for this relativistic transformation, what we want to include here is J mu as essentially our gamma, rho naught C and velocity V. But this means this is essentially the rest. Charge density. And this 4 vector, gamma, C, and V, this was our relativistic velocity vector eta. Right? So we'll see that we can write J mu just as a 4 vector as the rest mass charge density times the Lorentz for velocity eta. Alright, now let's see how that connects. If we have, so look for example here at divergence E equals rho over epsilon naught. Divergence E is essentially the divergence here of the first row of the field tensor. It seems to suggest, so if we start from divergence E equals rho over epsilon naught. Divergence E, of course, is df0 mu over dx mu. Right? This is the essentially divergence contracted with this 0 line. Right? But this is 1 over epsilon naught. This is modulo factor C, the 0 component, right? So this is essentially J, the 0 component. So there is factor C here. So it's C times this. But so E, there is actually E over C. So this is C times so this is 1 over and if you figure out the other Maxwell's equations, what it comes down to is that we have df, so generally df mu nu over dx nu, equals mu naught j. You still need to figure out, so gradient E, this is 1 over C, this is that, and of course we have to divide by C, right? 1 over C, because J naught is C times rho naught. So we have just rho with 1 over C. So bring the 1 over C over here, gives us df0 mu over dx. Mu equals 1 over epsilon naught C squared, J naught, and of course this mu naught. Okay, so that is the postulate here. We see if that also makes sense, say for the one component, so let's say df1 mu over dx mu. So for 0, we have said it's the first Maxwell equation, df1, so this is this d over dx, this d over dt, d over dx, d over dy, d over dz. Right? That's what that says. So this is minus 1 over c dx over dx naught, right? Plus, so the 1, 0, and there's 2 d dx z over y minus dy over dz, right? Okay. Remember that it's not was ct, right? So what we have here is 1 over c squared dx over dt, and we have here dz over dy minus y over that. That is curl of B, the x component, and in fact this is a minus. And what we have on the right side is mu naught j, which would be 1, that is the x component of j. Okay, so write this in terms, so we have curl B, x component equals mu naught j, x component plus x over t, 1 over c squared is mu naught. So that gives us these equations. So this gives us the inhomogeneous Maxwell's equations. So this is exactly these Maxwell's equations. Then we have the inhomogeneous Maxwell's equations. We have, say, divergence B equals 0. This one is the divergence d over dt, d over dx, dy, dz of the first column here, right? The first row. So let us stay here. Next postulate is that we have the g mu over dx equals 0, giving us inhomogeneous Maxwell equations. So giving us this. The first row, so for 0, that's easy, right? So for mu equals 0 gives us divergence B equals 0. Let's say mu equals 1, then we have D, so mu equals 1. Then we have, so take the divergence of the first row here, dB over dt, minus dBx over c C dt, that's dx naught, right? Plus, we have a 0 here, and we have minus dz over c. So minus 1 over c dz over dy plus 1 over c dy over z equals 0. And you see is that this curl x component equals minus over dt. And you can do the other components in exactly the same. So it means Maxwell's equations, the connections to charges and currents with our 4-vector generalization of the charge current densities are simply written in this nice and compact form. It's a lot less writing, although when you actually want to calculate things, obviously you will go back and ultimately solve Maxwell's equations and not actually solve this. But it's a nice compact way how you see it all fits together. One other thing we can actually do with our 4-vector charge density, if we do something similar to this with our charge density, if we calculate dj mu over dx mu, so essentially take the 4-dimensional divergence of this. So this is then 1 over c dj naught, but 0 is rho naught c over dt, right? That is the 0 part of the sum, plus the rest is gradient j, right? Equals, what is that? The c's we can cancel out. Meaning, what kind of equation is that? We say the divergence of the current density equals minus d rho over dt. What kind of equation is that? What does that tell you effectively? Which principle is behind that? That's the change of charge density. It's essentially given by the divergence of J is current, essentially the flux of charges out into something. Right? So it's called continuity equation. And means if you integrate that over all space, that tells you charge is conserved. So that's called continuity equation. Okay. Just a little bit left to do. So the last thing we want to do is see if we can connect all of this to this nice description in terms of potentials. See, that's essentially how we started out. In terms of, say, writing electric fields as minus gradient B minus dA over dt, right, and B being curl A. And then we have calculated in a certain gauge, which gauge was that, in which we had the connection between charge and current densities and the potentials. That was valid for one specific gauge.
I think it's the Lorentz gauge.
That's the Lorentz gauge, very good. And it's only in that gauge that we then have fields and potentials calculated from integral. So from that, see, we had, for example, that E was 1 over 4 pi epsilon naught probably 3 r prime rho of r prime ct r and over times r prime t r of t r. That was all based on this Lorentz gauge there. So now let's see, and say A for charge current densities, right? Let's see how we can kind of fold all of this in with this field tensor here. The first thing we probably want to do, just like we did for charge and current densities, so we have a scalar here, B, and we have A. The first thing we want to do is that we define a 4-vector of the potential in terms of having a 0 component, just our scalar potential, for the units has to be 1 over c, and the 3-vector of the potential at t. Then, once we've accepted that, we can continue here. This. Next postulate that we'll prove now is that now we can relate our field tensor to these potentials as being dA mu over dx. Mu minus dA over dx. Mu. Right, for example, let's try to calculate the electric field, Ex. So this would be Ex will be C times F01, right? If this is true, then this is A, so mu is equals 0, mu equals 1, so C dA0 over dx1 minus dA1 over dx0. What is this? A0, and this d over c. So c times that is dv over dx. And A1 is the x component, so minus c d a x over c t. Sorry, I made one mistake here. The way this is to be written is in terms of these contra-element components. Remember that x0 was minus x0, x1 equals x1, and so on. If we have x0 here, in fact, dA. Sorry, this mu is a mu over dx. Mu, this is let's have the minus sign of everything. So minus, but here we have a minus sign. This way it works out. So this is minus gradient v x component minus dA. So, this gets us the first one. Let's say we want to calculate a magnetic field, so let's do the 1, 3. So mu equals 1, mu equals 3. Then we have Bz equals, so this is F1, 3, equals, so then we have this one here, 3 dA2 over d1 is x minus dA1 over y, so it's dAy over dx minus dAx dy is rho a. Right. Okay, so you see that this actually reproduces our connection between scalar and vector potentials. Now, one last step. If we want to now connect this to the charges and currents, then we want to figure out what is dF mu over dx mu. That is, well, if we now use this is d over dx mu. F mu was dA mu over dx mu minus dx mu, right? Or let's write this as d2A mu over dx mu minus d2A mu over x mu. Okay. Now we can switch these here and see what does the Lorentz gauge actually tell us. So the Lorentz gauge, what was the condition for the Lorentz gauge? Both gauges told you something about divergence of A, right? And the Coulomb gauge was 0. Lorentz gauge was minus 1 over c squared dV over dt, right? But what we have here, so if we have divergence A plus 1 over c squared dV over dt, if you look what that is, dV over dt, c squared, c, 0, c dt, c dx not, and then we have the divergence here. What we have here is in fact simply dA mu over dx mu, right? So the 0 component is, A0 is V over C dt, so this one, and the space component is that. But this contraction we actually have here. So if that is 0, just brought this over to the other side, that means this term then becomes 0 in the Lorentz gauge. So what we get from that, that means this equation then simply tells us that d2A mu over dx mu equals minus mu naught j mu. But what we have here, we have the contraction of the second derivatives over all components. What we have here is in fact nothing else but our D'Alembert operator. So this is nothing else but D'Alembert of the 4-vector scalar product, the 4-vector potential is minus u naught j mu. And really, pretty much all of electrodynamics is in there. Of course, actually, starting from this would not make any sense at all. And again, if you really want to do something and calculate something, you will go back to Maxwell's equations to actually evaluate. But you now see how it all falls into place. You see how electrodynamics is inherently relativistic. Everything you can write consistently in this covariant, contravariant, 4-vector, and tensor notification. Good. Maybe we can briefly discuss a little more on this next week. Otherwise, next week I want to go a little bit into astrophysical applications of radiation theory. And really, since most of you will probably be looking for master's projects sometime soon, maybe I'll give a little bit of an overview, maybe half an hour or so, of what's going on in high-energy astrophysics. Maybe some idea if you might be interested in doing something along those lines. Any questions on this? If not, then I'll see you next week.